So our final presentation is from MIT Lincoln Laboratory on D4M, and we have Vijay and Lauren here to present.
Thanks a lot, Eli, for the introduction. Well, first of all, thank you all for being here. I know it's the end of the day, but we're excited to be here. So what we wanted to talk about today was, we've been doing a lot of work with the Accumulo community, and in particular, we've been developing a technology called D4M. And many of you here have heard of this, and we've mentioned this many times. So what I wanted to do today was sort of do a deep dive into what D4M is, but more importantly, my colleague Lauren over here will give a brief demonstration at the end of how does this work? What does it do? And how can I use it? So what is D4M? Since we're at the end of the day, I want to give you the 3 points. One is it's a popular open source software tool that connects scientists with big data technologies, and this has been a popular piece. The D4M Accumulo binding, which is of interest probably to this group, provides a high-performance connectivity to Apache Accumulo for quick analytic prototyping. And finally, this is a new research area that we're very excited about called Graphulo, graphs in Accumulo. And the idea here is to implement BLAS, which is a spec, techniques on server-side iterators and operators on Accumulo tables. And I'll talk about this a little bit at the end because we hope to have a release of this software soon, and we would love to have your input in this. So with that, I think many of us are quite familiar with what the problems are, right? We have lots of data, and our users aren't really growing at the same pace. The Internet of Things, which is, for those who follow the Gartner hype chart, is sort of the new term, and that just increases the challenges associated with what were traditionally called the 3 V's of big data: volume, velocity, and variety. We've sort of been looking on an additional V called veracity, and yes, it doesn't exactly mean security, but it starts with a V, so we're going to stick with it. And so this is the sort of hidden 4th V, and we've been researching solutions and technologies that we can address these challenges. So earlier today, for those who attended my colleague Cass's talk, she talked about the big data architecture. And the big data architecture is something that we've been working in collaboration with the government in developing the different pieces of a system that you need to address some of the challenges that you have with big data. In order to address big data volume, which is really talking about the size of information coming in and the accessibility of this information, we've developed what we call the MIT SuperCloud, which provides an easy way for people to work with the different types of cloud environments that people may be familiar with. So you might want to do a big data cloud as well as a supercomputing cloud and combine some of these results together. And I'll give you an example of some of the work that came out of building the SuperCloud. Finally, and of course, this is very dear to us, is our work with Accumulo. And we've done a lot of work with validating this technology, and this has really helped us address some of the big data velocity problems, dealing with the information as it's coming in. Many of you may have seen this graph that I have on the bottom left of the slide, but this is our work in showing how much we can benchmark Accumulo and what type of ingest rates we can achieve when inserting data into Accumulo. Finally, we've been working with big data variety, and this is being done through D4M. And D4M is really a few pieces. Over here is an example of the D4M schema in use, and we've applied the D4M schema, which I'll talk about in a little bit more detail, to a diverse amount of data. Finally, we've been doing a lot of work with big data veracity. Earlier today, you may have heard the great talk that Cass gave on verifiable query results. We've also been developing tools called computing on mass data to address some of the challenges associated with securing or protecting big data that's in the cloud. So, with the motivation out of the way, let's get into what D4M is. So D4M, which stands for the Dynamic Distributed Dimensional Data Model, so D4M, is really a few pieces put together. There's a mathematical construct, which is associative arrays, which provides a data type for big data. There is a schema that can be used to take arbitrary data, most arbitrary data, and convert it to associative arrays. And finally, there's a set of software tools that you can download to not only work with associative arrays, but also to connect to back-end databases. So essentially, D4M binds databases to arrays and enables rapid prototyping of analytics and fast visualization. So to repeat, we've got three pieces in D4M. There's math, associative arrays, there's a schema, and there's software tools to do all of this, to be able to actually build these pieces. The software tools are currently implemented in MATLAB and Octave, and we have a prototype version in Julia, for those who are familiar with Julia. Just as a random, how many people here are familiar with Julia? So there's a few out here. Okay, great. We're very excited about that tool that's coming out soon. Right now, we have the ability to connect to databases via whatever interface it provides us. So to connect with relational databases, we can use the Java Database Connector, which is JDBC. To connect with databases that have a shim, so SciDB is an example, which is a multi-dimensional array database. Or we can build our own custom APIs. And in the case of Accumulo, we've actually built our own custom Java API. So the image on the left really shows what our goal is. We have database engines, we have D4M in the middle, and we have applications. Our goal, our dream, is really for application writers to not worry about what the underlying database technologies are, to be able to use this single language in between. While we do support quite a few databases, Accumulo is really the one that we pay attention to because of its versatility and the types of problems that we can solve with it and how near and dear this is to our customers and the people that we work with. So I'll talk a little bit about each of these three pieces, and they may seem disjoint at first, but when we get to the demonstration, hopefully you'll understand how all these pieces come together, because a lot of people are probably wondering, okay, there's math, schema, and software. Where do these come together? So what are associative arrays? Associative arrays you can think of as sparse arrays with string labels on the rows and columns. There are some nuanced differences between sparse arrays and associative arrays, but at a high level, that's an easy way to think about it. One of the key innovations with associative arrays is what we call mathematical closure, which means that when I apply an operation on an associative array, I end up with another associative array. And that has some useful properties, as Lauren will show in the demonstration later. The mathematical closure allows us also to have composable mathematical operations. So I can do traditional addition, subtraction, multiplication. I can do logical operations on associative arrays. And each of these result in an output associative array. We can also do composable query analytics via array indexing, which means that we can easily pull back pieces of a table, and that also returns an associative array that we can then put through different mathematical operations. And implementing associative arrays is relatively simple. If you have a language, if you have a programming language that has support for 2D arrays, sparse linear algebra, and operator overloading, we can actually do this pretty easily. And we've actually done this version of it in about 2,000 lines of code. And having a short code base is also of great interest to us because, as I mentioned, we work a lot with the data security and code security, and having less lines of code makes it less likely that there are problems in it. So associative arrays allow us to do very complex queries with often a lot less effort than you'd need using traditional programming languages like Java or SQL if you're using databases. It gives us very easy, natural, high-performance implementations. But however, you're thinking, look, I've got a text file of data that my sponsor or customer has given me. What does this have to do with associative arrays, and how do we actually move from one to the other? So we've developed what we call the D4M data schema, which actually allows you to take many arbitrary types of information and convert it to an associative array representation, which has all these cool benefits that I just talked to you about. So a schema is essentially a structure that's described in a language that is supported by a database management system. And we use the D4M schema to take heterogeneous data types and represent them all in a common data format. And essentially what the schema does is it converts structured or unstructured raw data text into a tuple representation that we can then connect with Accumulo. It has this one-to-one relationship with the associative arrays. We usually recommend using a four-table representation, which consists of what we call the edge table and the transpose table. I'll explain why we do that in a second. A degree table and the raw data table. So over here is an example of, so at the top of this chart, what I have is an example of a dense data table that you may have. And this may look familiar to many. You may have, you'll have a row number usually, or some sort of a unique row identifier. You'll often have tens, hundreds, perhaps thousands of columns. Some of these columns may be structured, some of these columns may be unstructured, and usually they're all put together. And the example over here is an example of how you take that dense data table and convert it to the sparse representation that we call an associative array. So the first thing that you can do over here is to create a unique row key. And many of you will understand why we need a unique row key. And you can create a unique row key using this representation by taking the row label and appending the row value. That generally creates a unique row key. Sometimes you might need to add another piece to make that unique row key. In order to create the different rows, you can take the column labels and append the column values to that. So you'll see that the first column of our associative array, or the sparse table of the T edge, is column 1 appended by the value of row 1, column 1. Now, for those who are looking at this, what we've essentially done is take all the semantic information of this dense table and stuff it into the rows and the columns of this sparse array. Now, that's great. If we're looking up rows only, this would probably work very well with Accumulo. However, very often, since we've put at least half of the information in the columns, we often want to look up the columns just as fast. So what we do, in addition to storing this main table, the T-edge table, we also store essentially the transpose of the table, in which the columns become the rows. So you can think of it as a flipped table. And what that allows us to do is do column queries very, very quickly. And this is actually a standard trick that's used in linear algebra. A lot of algorithms in linear algebra actually work on either the matrix or the transpose of the matrix. So very often, in order to save either the communication time or the operation of transposing, you actually just save both of them in memory. And then depending on what operation you're doing, you'll actually pull the right one in. And in fact, this is a trick that D4M makes use of. So we saw in the previous page, if you were pulling information back from a row, it would go to the main table. If you're trying to do queries on a column, it would actually talk to the transpose table. And this is actually done under the hood. So the user doesn't really need to worry about this. They just need to create a binding to a table pair. We've also found that it's very useful to create what's called a degree table. So it turns out that the associative array representation at the top is very similar to an incidence matrix for a graph. So summing across the rows, which essentially tells you how many edges are going into a particular node, gives you a degree of a particular vertex. So that's where the name comes from, and we call this the degree table. And what the degree table is very helpful for is it allows us to do some efficient query planning. It also allows us to avoid supernodes, and Lauren again will give you an example of what we mean by supernodes. But we've kind of learned that very often when people are doing these queries, they want to avoid the very popular and sometimes maybe the very unpopular terms. So the degree table allows us to figure out the popularity of certain terms in our data set, so you can do some interesting query planning operations. And finally, you'll notice column 3 on the dense table, so all the way at the top, is an unstructured column, and what we've essentially done is break it up into 1 grams. So we've taken column 3, appended it with word 1, column 3, appended it with word 2, and created the new columns in the main table. What that might often do is mess up the order of the words in column. So what we also do, and this is what we call an auxiliary table, is just store a 4th table that has this raw unstructured text in it, again indexed by the same row key that we used in our edge table. So what we have now is, we've talked a little bit about what D4M is, we've talked about associative arrays, and hopefully we've been able to understand how you could take that text or CSV document that you have and convert that to your application. So now what we'll go into is a little bit of detail on the D4M software library. We have a lot of details here, and what I want to do is be able to go through some of these, and happy to have deeper discussion on any of these pieces that people are interested in after the talk. So the associative array representation that I talked about works very well for different types of database. In fact, it even works as a great interface. So you can think of actually casting information from SQL to Accumulo, Accumulo to SQL. using this associative array implementation. And we currently have implemented D4M to work with associative arrays in a variety of languages that support sparse linear algebra. So I mentioned MATLAB, Octave, and Julia, which we have an early version, and it's sort of in progress. And so this is something you can download. So you can go to d4m.mit.edu, and there is a tarball that you can download. You can expand this tarball, and you get two pieces that come out of this. You get the D4M API, which consists some of the MATLAB source, as well as the D4M jar that does the connection to Accumulo. And we also have different dependency jars that you may want to, say, connect with JDBC or other databases as well. I'll talk to you specifically about how we're doing the Accumulo piece. So this is very easy to use. You can download it if you have one of the languages that we're supporting over here. It's really just adding path. There's no other dependencies. If you want to connect it with Accumulo, it's usually a couple lines of code. You really point it to the host and the port and give it a username and a password that you have for Accumulo, and you should be ready to roll. So when you're using Accumulo, this is what you see. You typically take your data set, you convert it into a triples representation, so you have a row, column, and a value. You can use the MATLAB D4M API, or any API, to convert that into associative arrays. You can use the D4M Java API to actually insert this associative array into Accumulo, and that calls the Accumulo Java API, which then does the final insert into an Accumulo table. So to create an associative array is as simple as creating row, columns, and values, which can be done with strings, and calling the assoc. We're still trying to figure out how to pronounce this word, but we'll call it assoc for now, and feeding in the row, column, and the values. You can even provide a collision function for cases where you have the same row, column, and values, and you can tell it what to do when you have two of those things that come together. To insert this data into Accumulo, so what we've created in the first piece is A, which is an associative array with R1 with the row, column, and value from above. We create a connection we create a DB object calling the DB server operation in D4M. We point it to an Accumulo instance, a port, provided a username and a password. We can then create a binding to a table in Accumulo if it exists, or it'll just create a new table in Accumulo for you. We can use the D4M put command to take this associative array and just put it into Accumulo. And we can finally scan all this information by using a notation like colon, comma, colon. So what a developer sees is different pieces. So for people familiar with the internals of Accumulo and the Java API, there are many different pieces that you'll see. So just as an example, calling the db create function in MATLAB calls the Java class D4M db table operations, and this essentially creates a table in Accumulo. So all the source code is released and available. Please let me know if you'd like to take a look at this. What's happening in D4M right? Our associative array, we remember we had the row, the column, and the values. The rows go into the 7 tuples row, which makes sense. We take the associative array column and we stick that into the column qualifier place. And we take the associative array value and put that in the value. So this is what's going on when we're inserting into Accumulo. If we want to add something to a column family or put visibility labels, we can do that as well using the put column family or put security functions. Just some details on how we're actually doing the insert. A lot of this was determined by trial and error, but for those who are curious, we're doing 500 kilobyte batched inserts. So how we do a D4M scan is we can connect to a table and pull data back. We can give it row keys or column keys, and we can even do ranges of rows and columns at the same time, though usually we'd want to break that up into two separate pieces. We also have a way to connect to an Accumulo iterator, and we can do this by using the iterator object, and then create an iterator object, and then we can actually pull information back from there. So how do we do, so till now what I've been able to talk to you about is how we use D4M. We can connect to Accumulo, we can put things in, we can pull things out. We've also been able to connect this to our, I mentioned earlier about the supercloud and how we can do big data operations as well as supercomputing operations. And this is an example of actually doing some supercomputing operations. So what we're doing over here is doing a parallel insert. So we can have multiple clients inserting into Accumulo simultaneously. So in this example, what we're doing is we're creating a connection in the top to to a table pair, so the edge table and the transpose table. We're creating a mapping of what type of files we'd like inserted. And each one of our clients will essentially do a subset of the total number of files that they'd like to insert into Accumulo. And in fact, this combination has given wonderful performance, and it's actually given rise to probably a graph that many of you have seen a version of earlier in the summit of the rates of insert that we're able to get. So this graph, what we're showing over here, is as we change the number of server nodes that Accumulo is running on, so this is given by the different colored dots according to the legend on the top left. We're showing on the y-axis the number of database inserts per second, and on the x-axis the number of clients or processes that are ingesting simultaneously. So it was very interesting to see that for a 216 node instance of Accumulo, so we're running on 216 nodes, each with 32 cores, we were able to get about 115 million inserts per second when we had about 1,024 clients writing at the same time. So this is exceptional performance, and this is probably some of the highest performance that we've seen that's published in academic literature. So just to prove to you that we didn't just make these numbers up, here's a screenshot from the Accumulo monitor. And this shows a couple of things, really. So first, for those who are familiar, this shows the entries per second. So we'll see that we're peaking up around 115 million entries. You'll have to take my word for it there. The other thing that's very interesting is using this parallel load and D4M, we were actually able to get this steep incline, which is actually a very difficult problem in benchmarking, to get such a steep incline so that we're able to actually get to that 115 million entries per second. I'm happy to share more details about what changes we made to Accumulo in order to do this after the talk. So finally, and I know I'm behind schedule, but Lauren.
Hi, so I'm going to show how you can use D4M to do some quick exploration, analytics, and visualization, and show you really how easy it is to use this tool. So if you remember back in August last year, there was an earthquake in Northern California. So we went back and put a bunch of tweets from around this time period in an Accumulo database, and there were a couple million tweets in this database. So the first thing you need to do is set your bindings to the tables. You can do this in just 5 lines of code, which is pretty neat. So one thing that Vijay mentioned is we have both the edge table and the transpose table. We have something called a database table pair, which allows you to not have to think about which one you're going to be using in your queries. If you're doing a row query, it'll query the edge table. If you're doing a column query, it'll query the transpose table. We also have the text table and the degree table set up here. So we want to look at the tweets where people are talking about an earthquake in general. So we're going to query on the word earthquake. First, we're going to look through and find the column for the word earthquake. Once we have that, we have all the row IDs that mention the word earthquake, and we can go back into T-Edge and get the full tweets. And here you can see what a tweet actually looks like, all parsed out. So we have things like follower count, friend count, location, and we have all the words parsed out, and both the original version of the word and the lowercase version of the word. You can also see the size of this associative array A. The first number is the number of rows, and the second is the number of columns. And the number of rows are the number of tweets that the query came back with. And there's around 2,300 tweets that mention the word earthquake. So we want to look at where people are talking about the earthquake. So we're going to search by something called the geohash. Geohash basically takes a map of the world, breaks it up into boxes, and each box is given a character. And then within each of those boxes, we break it up again into more boxes. So you have a bunch of characters describing exactly where in the world that thing occurred. So to do this, you can simply just filter on everything that starts with geohash, and that'll give us all the geohashes, and we can sum that up to get the counts from each geohash. You can see there's almost 2,000 locations that people are tweeting from. Because our geohash is 8 characters long, it goes pretty small, like less than a mile about. So we want to look at places where people are talking about the earthquake a lot. So the locations that people have tweeted from more than 5 times are listed here, and you notice that each of them starts with WW, which in our geohashing scheme maps to Northern California, which is pretty neat. So once we have kind of the location that we're interested in, we can go through and actually filter on that location. So we can index into the associative array and get back only the tweets that were tweeted from the location that we care about. So we bring it from around 2,300 tweets from our initial query down to 1,500 tweets. And now that we have the locations, let's see what people are actually talking about in the area. So we can query the text table, which I did here. You just take the row IDs that are in the associative array A and query the text table. So because our row keys are approximately in chronological order, you can see the first few are people initially reacting to the earthquake, and then a couple more in, it's more people commenting about the earthquake that already happened. But this isn't too useful if you want to know in general what people are talking about. It'll take a long time to go through and read 1,500 tweets, and nobody wants to sit around and do that. So we're going to look at what words people are using and what words are being used together. First thing we want to do is remove stop words. Stop words are the words that we use all the time and aren't very helpful. So every tweet is going to contain either a or the, him, her, they, things like that. And they're just not helpful. And Vijay mentioned the supernodes, and these are the supernodes kind of in the words case. So we're going to go through. We have this nice function cat string, which allows you to append the column sort of name here to the front so that you're able to quickly get it into a format that you can index into your associative array with. And to remove it, it's a simple subtraction. I know Vijay mentioned the composability of associative arrays. It has closure, so we just do this subtraction from A, subtract the columns that have the stop words, and you get back this associative array, which isn't including the stop words. So you can see from the first size of the columns, the second one is about 150 words less, which is the size of our stop words. So now we can look at what words are going together. And this is one of the neat things you can do with D4M. So we're going to start by just getting all of the lowercase words, and then we're going to do a matrix multiply. I think Vijay mentioned that the kind of the natural form of an associative array is an incidence matrix. That's how we store it in Accumulo. You can take this incidence matrix, which is basically a list of edges, do a matrix multiply, and have an adjacency matrix after that. So you can see which words occur together. And in this adjacency matrix, each row and column maps to a specific word, and each value maps to the number of times those words were used together. So we'll look at just one of these words. We'll look at the words that were used with hashtag earthquake. And you can see there's some useful things in here. People felt the earthquake. It was the first one they felt, maybe. But you also see things like hashtag earthquake again and the word earthquake. Because we queried on the word earthquake, that's not really helpful. It's going to be in every single tweet. And every single tweet that has the word hashtag earthquake is also going to have hashtag earthquake. This is the diagonal of the adjacency matrix, if you're familiar with that. So we want to remove those because they're not helpful at all. And we can do this again just the same way we did stop words. You just use subtraction, and you get back your adjacency matrix with the words that you care about. So let's look at some words that occur together a lot. You can see I did the words that occur more than 50 times together and the words that occur more than 25 times together. We get things like last night, woke up, 6.0 magnitude, slept through, and then there's Bay Area, because it happened in the Bay Area. And this is really neat that these things just pop out very quickly, and didn't take me too long to put this together and get to this point. So once we do that, it's always fun to do some visualization, see where people are talking about, and see what they're saying. So again, the same way we did subtraction with the stop words and the diagonal, we can do addition to merge two associative arrays together. And there's nothing stopping us if they're different dimensions or anything like that. It'll just merge them together. So we can do that with A and the full text of the tweet. We have this nice little function that outputs your associative array into a KML file, so you can view it in Google Earth. And then you can kind of navigate around through Google Earth, click on tweets, see what they're saying. We have someone here who's talking about, I think the first time they felt an earthquake in San Francisco. Yeah. So next, VJ is going to tell you a little about kind of the ongoing work we've been doing and what's coming next, and kind of summarize everything for you.
All right, thanks, Lauren. So hopefully that quick run through of some pieces of D4M was able to show you how we can connect to Accumulo, how we can connect to databases, why we talked about associative arrays in the first place, because when you pull the data back, you have it in this format that you can now do subtraction, removing things, multiplication, which has some neat properties, and show you what the software tool and the API look like. So just to sort of provide you a summary, it's a popular, D4M is a software tool that's being used by quite a few people, especially people who are into rapid prototyping of analytics. The Accumulo binding gives us high performance connectivity to Apache Accumulo. And we've seen some great numbers using D4M in conjunction with high-performance computing or supercomputing techniques. I'm also very excited to talk about some of the new research that we have in expanding what Accumulo does to graph analytics. So Graphulo is an ongoing project, and first of all, thank you to many people of you who helped us design this create the design document that went around maybe a couple months ago. Your feedback was very, very helpful. We're very interested in hearing what the community has to say about these type of projects. So thank you again for the feedback. We look forward to having some software out there soon for you to play with. But essentially what we're trying to do in GraphBLAS is be able to make use of Accumulo's server-side operations to be able to do graph analytics directly in Accumulo. So you can think of the example that Lauren gave earlier of doing this matrix multiplication, right? Wouldn't it be great if we could do that matrix multiplication without having to pull the matrix back to our client, but rather we're able to do the operation directly in Accumulo? So this is the idea of creating a table that's similar to a stored procedure that I think was mentioned earlier today. So this is something we're very excited about. We believe that we'll get great performance from this, and we'll be able to do complex analytics. So the idea here is that you'd be able to do something like a breadth-first search directly in Accumulo. So I could say, I'd like to do a breadth-first search of this data and have it just output to another table. And I think that would be very powerful, because these are the type of analytics that people use, and this is the type of work that we really don't want to have this back and forth with the client operation. So we believe we'll get a lot of performance out of that as well. And you can, of course, pull the information back whenever you want. The idea, our first use case will be to work with queued analytics, which means that I want to be able to select, tell me the breadth first search of these certain nodes that are in Accumulo, that are in a table in Accumulo, and it's able to do the BFS of that and store that in an output table. Our aim is to have an Accumulo contrib project, and we'll be working with the community in determining exactly what's the best route for that and when would be the best time for that. We've released a design document for those on the Accumulo user list. Hopefully you've had a chance to take a look at it. For those who haven't had a chance to look at it, please let me know and I'll be happy to connect you to the document. Very soon, we're very excited to have an early version of the tools coming out in late May or early June. We're trying to call this a friends and family release. So if you're willing and being a beta tester for us, or willing and playing with these tools and providing us feedback, please let us know. We hope to have a much more developed version of this tool by the end of the year. And finally, we have a lot of future areas of development, even within Graphulo, even of this tool that we're still developing. We have been working with scalability, but we'd like to look at even larger problems, because we understand that the type of problems that we want this applied to can be anything. We've been wanting to work with different schemas. So while we use the D4M schema for our first version, we understand that people don't necessarily use that schema. And we also think that we don't want people to have to change their, here's a software tool, change everything you know, and then you can use it. So we'd like to be able to work with the different schemas that are out there. So if you have any thoughts on schemas that are popular and used by many people, please let us know, because we'd like to create the compatibility for that. And we'd like to create lots and lots of example algorithms that people can directly apply to their they can directly apply to their data sets. So if you again have algorithms that you're using that you think are used by many people or would be interesting, please let us know. We'd be happy to work with you to develop to work with that. And you can find out more about this at graphulo.mit.edu or by contacting either myself or Dylan Hutchinson, who I'm pretty sure many of you have spoke to. So of course, the work that we presented here was done by many, many people. And in closing, I'd like to say, first of all, thank you to the Accumulo community. You've been very helpful in any of these things that we've been doing. We've loved the communities, the vibrant community. When we have problems, they're solved very quickly. We get insight and feedback from the people who are developing and writing to this. So that's something we greatly appreciate. We also have a lot of opportunities at the lab for people who are interested in this work or the work that my colleague Cass talked about earlier today. If this is an area that you're interested in, we're always looking for students or experienced staff or new staff even who are interested in either internships. For those who'd like to rotate through the lab, we always are interested in having people, always interested in technical exchange. So with that, I think we're done. But I'd be happy to take your questions, and also happy to take your questions in person if you prefer. So thank you very much, and thanks again to the Accumulo community and to the summit organizers.